My name is Matthew Mules, and I am coming to you from Dallas, Texas. I'm presenting my thesis project over an up-and-coming alternative energy source, landfill gas. I was originally going to do an experiment to assign a kilowatt-hour per kilogram value to organic material, but COVID-19 kind of threw a wrench in my plans. Now my project is more of a research paper, and I'm presenting what I found. I hope you enjoy. Landfill gas energy technology. Let's first go into why we need landfill energy technology. As some of you probably know, we are facing a global climate crisis. Here are some statistics that I gathered up from NASA's website. Global surface temperatures are up 0.8 degrees Celsius from averages taken between 1951 and 1980. Global sea levels are up 94 plus or minus 4 millimeters since February 1993, and landfills are contributing to our methane production at 14.1% of total human methane production. Another really big contributor to our climate crisis is our energy sector. It produces 33% of our carbon emissions each year. Comprised of mainly non-renewable sources, our energy sector pumps 1,763 million metric tons of CO2 out into the atmosphere each year. If we are going to combat climate change, it is a must to reform our current energy sector. What exactly is landfill gas energy? Basically, we set up a system that removes the gases coming off of a landfill or garbage dump, and we purify the gases to get 100% pure methane and put that into a combustion engine or a turbine and use that to generate electricity that can go right into our power grid. So, unfortunately, landfill gas is not 100% methane. It's comprised of about 50% methane, 50% CO2, and then less than 1% of oxygen, nitrogen, non-methane organic compounds, carbon monoxide, and hydrogen. So this capture system here is set up, and the gas is transported through a bunch of different filtration methods. So a condensator, a scrubber, compressor. This will help remove other gases based off of their natural properties, chiller, reheater, another separator, condensing filter, and then after it's 100% pure, it goes into our engines or generators, and once electricity is generated, it can be supplied directly to the power grid. This isn't a completely new technology. Currently, out of about 3,000 landfills in the United States, 634 of them are using this system. On this graph below, you can see exactly which states house landfill gas energy systems and gives you a couple of stats about their productivity. There's 17 billion kilowatt hours produced each year by these landfills, and 96 billion cubic feet of this landfill gas is collected. So with about 50% of that gas being methane, that's 48 billion cubic feet of methane that is prevented from going into the atmosphere. And it's estimated that methane is about 28 to 36 times as a better greenhouse gas than carbon dioxide. So that's going a long way to help prevent the greenhouse effect. To dive a little bit deeper into the productivity of these landfill gas sites, 500 tons of municipal solid waste has an energy equivalent of 2,107 tons of coal with today's technology. About 72% of these sites are creating electricity that goes directly into our power grid, and 18% of these sites are directly offsetting non-renewable sources. It is clear that these systems can be efficient, and people have already started implementing them. But how much does it cost to get into one of these energy systems? There's four main costs associated with landfill gas energy systems: the initial assessments, gas collection and flaring systems, power generation systems, and operation and management costs. Initial assessments check landfill suitability for energy production. These tests cost generally in between $10,000 and $15,000 and check for the content of the landfill and the permeability of the soil. both which affect the ability for energy production. If the gas composition that the garbage is giving off is unknown, the price can be up to $25,000 because additional tests must be run. Next is the gas collection and flaring systems. These are paid for by acreage, and they cost about $24,000 per acre and have an operation and management cost of $4,100 every year. Lastly, you have the generator costs. Here's a table of the different types of generators that can be used, their wattage capacity, their average cost per kilowatt capacity, and their typical annual operation and management costs. Gas turbines can handle the most and are actually the cheapest, but not every landfill is trying to produce have a 3 megawatt system. So the smaller you go, really the more expensive it is. So it's more beneficial for these large landfills to use landfill gas energy systems than smaller ones. Let's take a look at an existing landfill gas energy system. The Frank R. Bowerman SLF landfill is one of the most successful LFG sites today. This landfill is 725 acres and is home to 55 million tons of trash. It also houses 7 Caterpillar CG260 internal combustion engines, is home to 30 employees, and has a 23.1 megawatt capacity. Some of the benefits is that it supplies 160,000 megawatt hours of energy to Orange County, California annually. It also eliminates the equivalent of 1.1 million metric tons of carbon dioxide each year. $25.1 million of electricity is sold by the Bowerman Company each year, and Orange County receives $1.6 million from the Bowerman Company annually for letting them sell their trash electricity. The cost of this plant was just over $60 million and has a yearly operation and management cost of $2.8 million. How does this stack up against coal and natural gas, though? Let's start with coal. Coal has a $3,500 capital startup cost per kilowatt capacity. A similar size facility to the one in Orange County, California would cost over $80 million to make. That's $20 million extra dollars right off the bat that you're paying for a coal power plant over a landfill gas energy plant. The same size facility would have a $23.1 million annual operation and management cost fee. That is an additional $20 million over the Orange County landfill gas energy system that you're paying every single year. When coal is excavated, it can also cause environmental degradation. And when coal is burned, it is the dirtiest fuel source. It is well noted that coal causes increases in respiratory disease rates in zip codes where coal plants are present versus where they are not. Natural gas is cheaper than coal power, but it still doesn't rank well against the landfill gas energy systems, especially the one that is exhibited in Orange County, California. Natural gas plants have a $1,789 per kilowatt capacity startup capital cost. A 23.1 megawatt facility would cost $41.3 million. That's a little bit less than $20 million to start a natural gas plant of a similar size. However, the operation and management costs of a 23.1 megawatt facility would be $13.9 million. So in the span of 2 years, the landfill gas energy system has already made its money back over the natural gas plant. And although natural gas is a fairly clean source of energy, it's generally obtained through fracking, which wreaks havoc on environments. So, where do we go from here knowing this information? We can tell based off the statistics from the Frank R. Bowerman SLF landfill that LFG energy is a viable replacement for other non-renewable energy sources. So what's holding it back? There's two main things: limitations of the system and knowledge of the system. Like I kind of touched on the initial assessment section of the cost of LFG systems, there's a limitation of garbage composition, permeability of garbage, landfill size, and continuous waste management. If the landfill is made completely of inorganic materials, there's no landfill gas to be given off to create energy off of. So it'd just be a waste of money to set up a landfill gas energy system on a plastic heap. The permeability of garbage also matters because the gas needs to be able to flow towards the gas collectors. So if the garbage is compact, it will not work. The landfill size is also a big factor. For the benefits to be able to be felt, these landfills need to be sizable. Also, smaller power generators cost more not only to build but also to upkeep. And continuous waste management also limits landfill gas energy systems. Say a plastic plant sets up right next to this garbage dump. If the plastic plant starts dumping heaps of plastic into the landfill, now this landfill gas energy system is less productive than it was, and a city that was relying on that power no longer has it. So how do we get all the landfills that meet the criteria to establish these systems? That's where knowledge comes in. I was going to originally do a experiment that would assign a kilowatt per hour value to a kilogram of organic material. I had the composters set up, they was all decomposed and everything, and I was going to collect the data after we came back from spring break. But as you know, we never came back from spring break, so that never happened. In my actual research paper that I submitted, I detailed the experiment and how one could conduct the experiment, so maybe it could be done in the future for a future honors thesis, which would be really cool. But experiments like the one that I detailed in my paper are really where these systems need to go. We need to have more knowledge on the topic so that investors are not afraid to invest in these systems, because as we can tell from the Orange County landfill, they're quite productive and cost not nearly as much as non-renewable sources do to operate and manage, even if there's a large capital cost right up front. Not to mention, we're eliminating methane that is eventually going to get into the atmosphere and breaking it down into less harmful carbon dioxide. So we're kind of killing two birds with one stone with this landfill gas energy. It would be amazing to see these implemented globally, because I really truly believe that if devices like these were implemented everywhere, we could make great strides against climate change. Thank you for listening. For those of you who care, here's my works cited, and I appreciate you tuning in. Once again, my name is Matthew Meals. Have a great day.